All right. I've become kind of obsessed with differential equations lately. So this um, is an example of a differential equation. And once I get this set up, it's this one. It's this one. Yeah. So what we have here is we have this tank. It's filled with a capacity of 70 liters initially. Sorry, the max capacity is 70 liters. It initially contains 20 liters of hot tea, and there are 15 grams worth of sugar in that tea. The hot tea containing 2 grams of sugar per liter is entering a rate of 3 liters per minute. The mixture is allowed to flow out of the tank at a rate of 2 liters per minute. So what we want to do is find the amount of sugar in the tank at any time prior to the instant when the solution begins to overflow. So let's write down what we have here. So we have volume max. What size is that? Use bigger size. The max volume equals 70 liters. We have, so volume initial equals 20 liters. Then say the quantity initial equals 15 grams. We have 2 grams of sugar per liter entering. So for this, I actually prefer to just set up a drawing. So let's set it up right here. Alright, so we have this tank, some flowing in, some flowing out. So what is flowing in is 2 grams per liter. That's the concentration of sugar. And the rate of flow is 3 liters per minute. Then flowing out will be I'll use a big C here, concentration in grams per liter. And the rate out is 2 liters per minute. So what you'll notice from this is that there is a faster flow rate in than what's coming out. So over time, this level is going to rise. And that leads us to the question is, find the amount of sugar in the tank at any time prior to the instant when the solution begins to overflow. So we want to know the amount right at the point when it's about to overflow. So we have, let's see, this is 20 liters. And this is 15 grams inside that 20 liters. And then this is 70 liters, the max amount. All right. So what we want to do here is we're going to set up a differential equation to model this. So the rate of change of the quantity of sugar with respect to time is going to be equal to the rate in, or what's going in minus what's going out. So Let me actually delete these. It really helps to think about the units. So the quantity with respect to time. Well, quantity here has always been in grams. Everything that I've given down here is in grams. And time is given in minutes. So we want grams per minute. Now if we look at what's going in, we see that if we multiply these two values, the liters cancel and that will give us grams per minute, which is what we want. So we have 3 liters per minute, which is our rate, times 2 grams per liter, which is our concentration, excuse me, minus the rate going out, 2 liters per minute, and then times the concentration. But concentration, we don't have any functions for concentration, but we see that concentration is equal to the thing that's in grams, which will be the quantity, divided by the things that's in liters, which will be the volume. So we're going to write Q in grams divided by volume in liters. And now a quick check of our units. We see liters cancel, liters cancel. So grams per minute minus grams per minute equals grams per minute. So the units check out. Now, so Q is a function of time. The quantity changes as time changes. Volume in this case is also a function of time. The volume changes as time changes, because as time changes, this is going to be filling up, so the volume that we have will be greater. So we need to find the end goal is to solve this differential equation for Q, to find a function of Q. But for now, in order to solve that, we're going to need to find a function for volume, and that's relatively simple, so that we can just kind of just think about it and come up with that. So volume as a function of time is equal to, it's going to be our starting value, which is 20. You know what, let me do the units thing again. So the units should be liters. So volume is going to be equal to 20 liters as our starting value, plus something times t, most likely. We see that this is going to be linear. The change will be linear, meaning that it will steadily increase over time. And we happen to know that the change will be related to the rate in minus the rate out. So the rate in is 2 grams per liter. Oops. Minus the rate out, which, no, sorry, not grams per liter. 3 liters per minute, that's the rate in. Good thing I did the units. 3 liters per minute minus 2 liters per, that should be minute, times time, which will be in minutes. So once again, doing our unit check, we see that liters per minute minus liters per minute will lead us with liters per minute. Then when we multiply times minutes, the minutes will cancel. So this is liters. So we're going to have liters plus liters, which gives us liters, which is what we want. So the units check out. So now let's clean this up a little bit. And now I'm not going to worry so much about the units. I know that everything is set up, so I don't need to pay attention to the units at the moment. Three times 2 is 6. 2 q over volume is 20 minus t. No, plus t. 3 minus 2 is 1, so plus t. So this is our differential equation. Let me just rewrite it again here and move this to the other side, because what we're going to do is we're going to use the integrating factor technique. So the goal, I'll write it down here, is to get our equation to look like dq dt plus p of t times q equals g of t. And then so p of t is there, g of t is there, and we're also going to from that figure out mu of t, which is equal to e raised to the integral of p of t dt. Then we're going to say we're going to multiply this mu of t times all three of these terms. So we'll have dq dt times mu of t plus p of t times q times mu of t equals g of t times mu of t. Now the reason for doing that was because on the left hand side, the this you use the reverse of the chain rule, and you can see that the derivative with respect to time of q times mu of t is equivalent to what we have on the left side there. I just finished writing it out. So if you take the derivative of this by the product rule, you see that the derivative of q is dq dt times this without taking the derivative, mu of t. And then over here, we're going to say that the derivative of mu of t is equal to p of t times mu of t. And that's true because of how we defined mu of t. And then q then will become not the derivative, so just like the regular. So that's the goal, that's the end goal. So we have dq dt plus 2 over 20 plus t times q equals 6. And we see from this that mu of t, we'll do this over here first. Yeah, we'll do this up here. So mu of t is going to be equal to e to the integral of, so p of t is this, 2 over 20 plus t. 2 20 plus t dt. So let's just solve this integral. I'm not going to rewrite everything every single time, but let's just simplify this integral. So we have 2 times the integral 1 over 20 plus t dt. U, we want to use u. Yeah, u equals 20 plus t du equals dt. So we have 2 times the integral 1 over u du. So 2 times the natural log of the absolute value of u, but for u I'm going to fill this in. 20 plus t, and there would be a plus c on the end, but we're not going to worry about that right now because in differential equations you typically only put that at the very end step. So, and this will be e raised to that power. So this is our mu of t. This mu of t. And I already wrote down here what we're going to do. So let me just rewrite p of t equals 2 over 20 plus t. G of t equals 6. Now I should be able to get rid of all of this. So now I'm just going to put it in this form that I already showed down there. So we're going to have the derivative with respect to time of q times mu of t, which is e to the 2 natural log of the absolute value of 20 plus t equals g of t, which was 6, times mu of t, which is e. Oops. I should have actually simplified that first. I'll just do it in the next step. This simplifies 20 plus t. Now, what we can do is integrate both sides with respect to t, because the integral of this derivative is just the thing that's in the parentheses. So that's really nice. dt. So we're going to have q times, and let's go ahead and simplify this. This simplifies to 20 plus t raised to the 2, because e to the natural log of something, you just bring that something down as the base, and then whatever was multiplied by it has to stay up in the exponent. This is equal to 6 times the integral of this thing, 20 plus t. Technically, I think we need our absolute value signs there, but I'm not going to worry about it because they won't come into play for the way that we model this situation anyway. We're only concerned at the moment with positive time anyway. So in order for this to be negative, we would have to have negative time, and that time would have to go below 20, which is actually nonsense in this, because that means if our volume goes below 20, then we've already emptied it out. We can't actually go any less than that. So yeah, so let's solve this integral. I'm going to use substitution again. I'll write it off to the side here. U equals 20 plus t du equals dt. That was very convenient. Q times 20 plus t squared equals 6 times the integral of u squared dt. Yeah, so q equals q of t. I'm going to go ahead and divide both sides by this. So we have 6 over 20 plus t squared times u, except I'll go ahead and fill in the u. U is 20 plus t, so 20 plus t cubed divided by 3. So let's get some more space. So Q of t equals, this becomes a 3 on the top. 6 divided by 2 is 3. This one and this one cancel out, so this is just 20 plus t. And then we can actually distribute that. So we have Q of t equals 60 plus 3. Oh wait, I forgot the c. There's where I needed the c. Thought something didn't look right. I was like, where's the e at? So this, taking a couple steps back, this was supposed to be plus c, and when I divided by 20 plus t squared, that distributes to both terms. So we have a term 6 times u cubed over 3 is one term, and then c is the other term. So this has to go to both. So this is going to be, c will be over 20 plus t squared. There we go. That looks better. Q of t equals 2, 6 divided by 3. 2 times 20 plus t, and then plus this, plus, we'll call this c times 20 plus t raised to the negative 2. So this is our solution, but let's solve for c, which we can do because we know that at time 0 we have 15 grams. So the quantity of salt at time 0 equals 15 grams, which is equal to 2 times 20 plus 0 plus c times 20 plus 0 to the negative 2. So this is going to be 15 equals 40 plus, that should probably be 400, but let me double check it on a calculator here. Come on. 20 squared. Yeah, 400. So 40 plus c over 400. So divide by 40. 15 divided by 40, and then we're going to multiply by 400. So one of these cancels with one of these. The 4's cancel. This is equal to c. So that, if this is 4, that would be 10. 40 divided by 4 is 10 times 15 equals c, which is equal to 150. So let's clean this up a little bit. All right. So back to our equation, we have Q of t equals, let's distribute that too. So we have 40 plus 2t plus 150 times 20 plus t raised to the negative 2. Now this is our final solution that tells us the the way that the salt changes over, the way that the sugar changes over time as this container fills up with this liquid that's pouring in versus the liquid that's draining out. And if we graph this, so let's go ahead and graph this real quick. So I'm using Desmos. I really like their software. I should actually point out this example more or less came from a textbook. I'll probably leave that in the comments. I didn't like the book while I was taking the class, but I really like the book now as a review after the fact. I think it was just too much for beginner level. So where's our zoom? All right. So this is what we have here. That's not super helpful, but this is our function. This is a graph of our solution starting at time 0, because anything before time 0 is kind of, we weren't trying to think about that actually, and up until the point when the tank fills. The question is, at what time does the tank fill? So to figure that out, I might have erased equation we needed, but it wasn't so hard to come up with. So the tank fills when the volume is equal to 70. So let's go back to our volume equation. And it actually ended up staying. It was 20 plus 3 minus 2, which is 1 times t. So when this is equal to 70, that value of t is the time that this fills. So 70 minus 20, so we have t equals 50 minutes. So this is the time that we're concerned with. And obviously you can plug that into the equation above, or we can solve that graphically here by graphing x equals 50. And we can see that our solution is 140 grams of sugar is the amount of sugar that will be in the tank when it fills, given the constraints that we were given.